Okay, good afternoon, everyone. Let's get started. So in the last lecture, we talked about the basic concepts in information theory, right? The definition of entropy. We started with the discrete random variables, and by using a logarithm, negative logarithm probability to represent the information for a random variable can take. Then we take expectation of that information. We give the entropy, right? And then we extend it to the, maybe I should go to, then we extend it to the continuous random variable, right? Continuous random variable, we follow the idea of the discrete random variable. We first discretize the random variables, right? By using some bin size delta. And then we kind of like map this continuous random variable to a discrete random variable, namely this y variable, like its value is 1, meaning that, okay, x falls in bin 1, y equals to 2, x falls in bin 2, and so on. So we can compute the entropy of this discretized random variable y, and then we just look at if your bin size takes to 0, like what's the limit of the entropy? Is there any meaningful result, right? So it turns out that if you do this, and if you take the bin size to goes to 0, then your entropy of the continuous random variable will be infinity. Okay, so because you got the negative log bin size delta here, so that's reasonable as well, because a continuous random variable can take many possible values. So it's naturally its information, contained information is infinite, but we can still compare with the information for different continuous random variables, because the first term, when we take the limit of delta goes to 0, we can find some reasonable and finite measurement, right? So we find that actually, if we take a limit of this summation of p of xi and this bin size delta and logarithm p of xi, when delta takes to 0, it becomes a Riemann integral, right? So that's kind of like our, when we learn the basic calculus, this how the Riemann integral is defined. And there's an alternative integral definition called Lebesgue integral, which is more robust and is less ill-posed, which in the future you might be able to learn them if you want to learn some matter theory, right? But anyway, when we do this limit, we can obtain a so-called the differential entropy, which is a negative integral of the density of x applied with logarithm of x, right? So an important of differential entropy is that it could be negative, because it doesn't really represent the whole entropy. It just represents one part of the component in the entropy of continuous random variables, right? And based on this entropy definition, then we can define the conditional entropy, and then we define the KL divergence, right? So KL divergence is also called relative entropy. So basically, it is compute between two distributions P and Q, right? So when we denote KLP and Q, it means you want to compute the KL divergence from P to Q. So you can roughly view it as a measurement of difference or distance from P to Q, right? So it's defined as follows. So it's negative integral of P of x, then a logarithm fraction between Q and P times d of x, okay? So well, if you look at the original definition, you can view it as the subtraction of these two integral, right? Px logarithm qx subtracted by negative px logarithm p of x. So from coding theory perspective, you can view it as, okay, what is the KL divergence actually measures if you want to transmit the information in coding P, but you instead use Q to transmit how much additional or actual information you will need, because you don't really use the target distribution P over X to do the transmission. You use an alternative alternate distribution Q, right? So of course you will need more information, you need more resource, right? And KL divergence measures the difference, right? The additional resource you will need to do such kind of transmission. Right? So some very nice properties of KL divergence. First, it is always non-negative. Okay, and when KL divergence is 0, if and only if P and Q are the same. Okay, so I will suggest you to prove it by yourself. You can just use the Jensen's inequality and convexity of the log negative log function as relatively straightforward. But rigorously speaking, we usually cannot say like KL divergence is distance, because distance has an important property that it must be symmetric. Right? So distance between A and B should be the distance between B and A. But for KL divergence, it is not symmetric. So meaning that if you want to compute KL divergence from P to Q, is usually different from the KL divergence from Q to P. This is not very perfect measurement of the difference of different distributions, right? But because of its nice properties and also easy for the computation, it is used in many approximate inference algorithms. And someone might ask, like, why not just define a new divergence which can be a valid distance? For example, I can define the distance between P and Q. Sorry. By the average, right? By the average of KL divergence from P to Q plus KL divergence from Q to P, right? Yeah, this is definitely doable. But if you use this kind of measurement to do approximate inference, you will have a lot more computational burdens, right? And there are even larger family of divergence measurements called alpha divergence. So KL divergence turns out to be a special instance of the alpha divergence family. So KL divergence plays a key role in approximate inference, which we're gonna discuss later in this semester. And we can see that actually all the determinist approximate posterior inference methods aims to minimize the KL divergence between the true and approximate posterior, all in the reverse direction. In general, we have alpha divergence, as we just discussed, and we discuss this in details later. Okay, so next, very important and commonly used information measurement is called mutual information. Okay? So, as the name suggested, mutual information means that, okay, how much information do two random variables share? Right? If you use a figure to show this idea, right? So you can represent a random variable X by one circle, another random variable by another circle. Right? So the mutual information is actually the part that overlap. Right? The two random variables overlap. Right? So you can view like, okay, what are the shared information of these two random variables? So now I want to ask, if X and Y are independent, what is their mutual information? I heard that. 0, right? Of course, if they're independent, there won't be overlap, and then the mutual information is 0, right? So let's see what's the algebraic definition of the mutual information, right? So it can be represented by the KL divergence from the joint distribution of x and y and the product of their respective marginal distribution. Right? So obviously, if x and y are independent, then the joint probability will be the same as px times py, and then you can see that the chiral divergence between two identical distributions simply be zero. Right? You can see that, right? But you can also just look at the explicit form, right? So it is an integral, double integral, negative double integral, the joint density of p of xy, and then log fractional between the product of px and py and the joint probability pxy, right? And it is not hard to show that the mutual information can be computed by the marginal entropy subtracted by the conditional entropy. Okay. So this can be explicitly told from this diagram, right? So we know that this overlapping area can be computed by the whole area of x, right? Which is essentially the entropy of x, subtracted by the conditional entropy of x given y, right? The conditional entropy of x given y is actually the part of x that do not overlap with y, right? So of course, the overlapping part is the whole area subtracted by part that does not overlap, right? And similarly, you can compute mutual information by the entropy of y subtracted by the conditional entropy of y given x. So again, I will leave it as an exercise for you to show that. So now we have covered the commonly used concepts or definition, information theory. Right? So we expect that you know the definition of entropy, right? What's the discrete? What's the entropy for discrete random variable? What's the entropy for continuous random variable? And just be careful for the continuous random variable. It is called differential entropy. Okay? And how is differential entropy derived? Right? And we need to be aware that entropy is an indicator for uncertainty. That's why those information theory measurement is very, very useful, like in active learning, like in Bayesian optimization, because in those cases, you always need to trade off the exploration to the exploitation, right? So what is exploration? The more uncertain I'm about this target function values or whatever quantity of interest, the more valuable to explore that, right? And exploitation means, okay, given my current model, which part of prediction I'm most confident, right? So those practical applications or problems always need you to trade off, make a trade-off between these two parts, like exploration and exploitation. Now, how do you evaluate which part is valuable for exploitation? The uncertainty, right? So that's why like entropy or mutual information are so important and useful. Again, we're going to talk about them more concretely when we meet that kind of specific models and algorithms. And KL divergence, the properties, especially be aware that KL divergence is asymmetric, and also definition of mutual information. Okay, so far any question? There it is. It's not ideal. The KL divergence is just for computational convenience. Yeah, it's just easy. As we just discussed, right? You can define a if you feel upset about the asymmetric property of KL divergence, maybe you can just define distance, a reverse distance, as the average of the KL divergence from P to Q and Q to P. Of course, it satisfies all the necessary properties for distance. However, if you use that as your basic measurement in approximate inference, it will bring a lot of troubles for your computation. That's the only reason. Okay. And of course, like a few research, maybe 5 years ago, they tend to like expand the family of divergence, like using alpha divergence, or even including this kind of like symmetric distance management, and how to develop more advanced approximate computational technique to overcome computation issue. Indeed, there are kind of such kind of research works, but it's not popular. The reasons that people always tend to use a simpler and easy approach. Right? Even in theory, they look a bit unsatisfying or awkward. Other question? Okay, great. Oh, by the way, if you want to look at more details, and also extend what our discussion in the class, in our course website, like in the lecture page, if you notice, there's a column like reading materials. I actually give the link and PDF that you can that will refer you to read them. Like that will give you more details about that. But in most of the cases, like if you feel comfortable with what we have discussed in the class, you don't need to look at those materials. But we put the link there in case you want more self-study or you want look at something from scratch. Okay, so next we're going to talk about what is the underlying philosophy of Bayesian model, right? And how do we construct non-informative priors? Right? That is to like defend the rationality of using Bayesian framework. Later we'll discuss like Bayesian framework is often criticized in that, okay, putting some priors too subjective, right? So what if I want to do objective Bayesian, right? So that leads to the so-called non-informative prior. Then we'll introduce a very interesting property in Bayesian framework. It's called exchangeability. It's actually the cornerstone of the modern Bayesian model. Right? So once we have a finished introduction of this, that means we have introduced all the necessary basic units, ideas, and frameworks for Bayesian modeling. Then we're going to move to specific models, the framework, and algorithms. Okay. So first, we're going to talk about. We're going to highlight the difference between the Bayesian view and the frequentist view, right? And I believe for most of the textbooks, especially for the undergrad course, students will always start with the frequentist point of view. But actually, from my own viewpoint, I feel like Bayesian view is more natural and intuitive. But by highlighting their difference in connection, we can better understand why Bayesian choose that kind of framework. And then we'll talk about uninformed priors. Then we'll talk about the exchangeability, the definition of exchangeability, which is based on the so-called definite theory. Okay. So to explain the difference between the Bayesian guys and the frequentists, right? So let us consider a general like model estimation problem, right? So we want to estimate some parameter theta, right? For example, the chance that you see a head when you toss a coin, right? Through some observed data set like x1 to xn, obviously we can assume x1 to xn are kind of RID, right? So, so there are two types of approaches. If you're a frequentist, you're going to view this parameter theta, like the chance that you see a head when you toss that coin, toss this specific coin, as some kind of fixed, constant numbers. It doesn't have any randomness. Like for example, give me this coin, right? According to its, material design, all kinds of stuff. I believe that okay, there's some kind of underlying chance tells us that okay, Gaussian quorum, how likely it will show the heads up, right? Maybe it's chance just 0.7, but we don't know it yet. How can we estimate that, or how can we approximate that? We're gonna toss the quorum for many times, and we just look at okay, among the total number of times, how many the heads show up, right? How many the tail show up? And I calculate the ratio. I use that ratio as my estimate of this unknown yet constant chance. Okay? This is a frequency point of view. So, and also explains or verifying the maximal likelihood estimation. Right? So I want to estimate this fixed parameter theta by maximizing the likelihood of the data given the theta, right? So then there's a problem. Like, how can I make sure my estimation is accurate or not? Like, in other words, how can we quantify my uncertainty about my estimation? Like I threw the corns for 10 times. And I observe like 6 has up, like 4 fills up. Okay, my estimation is 0.6. Are you very sure about 0.6 is close enough to the ground truth? See that? Not very sure, right? So an intuitive idea will be okay, I'm gonna throw it more times, like I threw it 100 times. Now maybe I observe 64 times heads up, and the remaining are tails up, right? So then my estimation will be 0.64. Then this estimate should be more accurate, or I should be more confident that the latter estimate is closer to the ground truth, right? Okay. That's our intuition. And if you have taken any statistics class before, right, we have some kind of like framework to quantify the uncertainty about the estimate, which is called confidence intervals, right? Does it make sense? Right? So use confidence intervals, which you're gonna view this maximum likelihood estimate as a random variable. You see what is the interval that your maximum likelihood estimate appears with 95% chance. Okay. So this is a frequency point of view. Okay. The key idea is that whatever parameters of interest, I always view it as some constant, although I don't know it. And my goal is to use a variety of approaches to approximate and to reduce my confidence interval. Does it make sense? Okay. Honestly, when I was an undergrad student, when I learned this, I really took some time to understand the whole procedure. To me, it's really unintuitive. So now let's look at how Bayesian people deal with this. So in the Bayesian world, the data itself, the observations, and whatever parameters of interest, they are all viewed as random variables. Right. So here, theta, the chance that you see the head of the toss coin is also viewed as random variable. And then how do you do that, right? We're going to consider a prior over theta. And then I'm going to integrate the data information through the likelihood. Then we seek for the posterior distribution of the theta given your observed data. Then this is max. So you can see that one big difference from the frequentist method is that, okay, we're not only seeking for a point estimate of theta, right? We're actually looking for a posterior distribution of theta. So once you have this posterior distribution, well, okay, you can get whatever point you want. Or for example, you can find out the value of theta to maximize the posterior distribution of density, right? Or you can use whatever, like posterior mode or posterior average, whatever. Okay. And meanwhile, if you want to quantify the uncertainty, you just look at the posterior distribution itself, right? Because the distribution itself contains all kinds of uncertainty about the value of state theta, right? So now we can see the key difference, right, between Bayesian and frequency state. So in the Bayesian world, everything is random. Every variable is a random variable. The only difference of those random variables are some random variables are hidden. You don't observe them. Some random variables are observed. Those are data. Right? We can roughly, we will like, okay, I got a random variable theta, which are hidden, and which are something I'm interested to aim for, right? And we have some random variable, which is not hidden, which have been observed, right? So my goal is that, okay, given this observed random variable values, how can I aim for the distribution of those hidden random variables? That's the basic philosophy. Any question? Is everyone comfortable? Honestly, when I was a grad student and when I look into the Bayesian learning framework, I said, okay, I feel like, okay, this is my favorite. I like this framework because you will everything. That's kind of the same in the nature, right? Only difference is that whether they are observed or not. And the do everything is that, okay, my goal is just to compute the posterior distribution. Like my prediction, my model estimation, all of them are just compute posterior distribution. That's it. Right? Then the key task is, okay, how can we effectively and efficiently compute the posterior distribution? That's it. So in addition to that, right? In addition to the intuition, right? Why the view of the theta as variable is important, right? So first, we can encode our beliefs or previous experience and desires in the prior, right? So the frequency point of view, well, it's weird to, or is this at least inconvenient to add any your prior knowledge about theta, right? But in the Bayesian framework, you just specify prior, right? You believe it's more likely to, theta is more likely to be between 0.6 and 0.7. You might just construct a beta distribution that reflects your beliefs, right? And then after the posterior inference, you can make a probabilistic statements of theta, right? What is mean, what is variance, what is quantiles, all kinds of stuff, right? Those are important in practice, right? But if you use confidence intervals, you can just tell you, okay, this is the region where most likely the ground truth will appear, right? So who can tell us what is mean and variance of your estimation of theta? Okay? There's if you want to do that, okay, for any probability statement, you might have to develop a new way of computation. It's different from confidence intervals. It's not very convenient. And thirdly, is that we can even make a more robust estimation of prediction. Right? So if you have model parameter theta, right? So if you just get a point estimation as what the frequencies do, so when you have a new input x star, right? If you want to predict so if you want to make a new prediction, right? You're gonna use your current estimate of theta and make a prediction. Right? But if you're using Bayesian perspective, we know that, okay, I got a posterior distribution of theta, right? With the data D, right? So that means my candidates of theta is not one. It's got actually infinite many. So I can kind of like average all possible predictions according to the posterior distribution. And in this way, I expect to get more robust prediction, right? Rather than just relying on one particular theta choice, right? Or theta value. So this prediction is called a predictive prediction or Bayesian prediction. But the flexibility of incorporating priors in a Bayesian analysis also brings up some kind of argument, right? So people will say, okay, you're so easy to incorporate the prior distribution, right? And then it can inevitably bring some kind of subjective bias, right? And subjective bias might be good for social science or artificial intelligence, right? Because artificial intelligence kind of like bring your prior bias with integrate prior bias with some kind of new knowledge together to update, right? That's reasonable. However, if you are doing some kind of like science, right? And we don't want our prior to have like a bias towards something. Right? We want our prior to be less informative, to be as less informative as possible. Right? So then that leads to how do you select an objective prior? People call it an uninformative prior. Like if you use uninformative prior, if you try to construct uninformative priors, right, and let the data to speak for itself, then this type of Bayesian analysis is called objective Bayesian. And also, although like frequentist models looks like they don't have any prior or something like that, but implicitly they make assumptions as well. Okay. But whether using frequentist Bayesian models, just check the assumptions you make. Okay. So I mean, if you want to be neutral, you don't need to like you know, particular favor Bayesian and then say if the frequentist is not good or in the opposite way. Okay. So you can be more like practical reason. You can choose whatever type of methods you like, and you just need to make sure what kind of assumptions you would like to adopt. Okay, any questions so far? David. What's the kind of not forming the learning method? Yeah, that's a very good question. That's the topic we're going to discuss next. But other than that, any other question? So is everyone clear about this Bayesian philosophy, right? Okay, so next we're going to talk about uninformative priors, right? So how can we construct a prior to be as less influence on the posterior as possible? That's the goal of objective Bayesian, right? So why do we need uninformative priors? What's the motivation? Right? So in many cases, we have little idea of what form of distribution should make, right? So we have already learned the conjugate prior, right? But as we emphasized, conjugate prior is purely motivated by computational convenience. And from a modern perspective, it doesn't bring much more. It doesn't bring much justification or rationality. So in the objective Bayesian field, right? People want to be as unbiased as possible, meaning that we prefer priors which has little influence on the posterior distribution. If you can construct such prior, it's called uninformative prior. But here, I want to emphasize that we just want to minimize or has this influence on the posterior distribution to be as less or as little as possible. That doesn't mean like it doesn't have any inference. This is practically very, very uh, rare that we can construct a totally no uniform Q prime. So people call it uninformed Q prime. Really doesn't mean like it doesn't have any information at all. It just tries to reduce the information and bias inside the file. Okay. And the goal is actually to let the data speak for themselves. Right? Don't try to bother them. Right? Just like let data decide and let the data speak. So now I want to ask, like, to construct such an uninformed prior, which part do you come out in your mind? Any thought? If you want that prior distribution over theta has least bias constant. So constant corresponds to what kind of prior distribution? Yeah, uniform, right? So obviously, is a first natural intuitive choice will be the uniform distribution. Okay. And if you're the idea is that, okay, since I do not know which parameters is more likely to be sampled, right? Or to be the ground truth, let us just assume the chance are equal, right? That's the key idea of uniform distribution. Right? So if your random variable, say, suppose your random variable is lambda, right? Given lambda, you sample x or you observe x, right? So if lambda is a discrete random variable, has finite number of the values, right? The uniform distribution will be just 1 over k. K is the number of possible values lambda can take. Right? If lambda is inside an interval, say between a and b, right? So we know that the density is 1 over b minus a, right? But what if lambda is unbounded? Meaning that, say, lambda is belong to negative infinity to positive infinity. Yeah, I mean, from the reverse definition of distribution, then you actually don't have such a uniform distribution because you cannot guarantee that the interval of the density will be 1, right? Will be unbounded. It will be unbounded, right? In this case, we just will P of lambda, the prior of lambda, is proportional to some constant. And of course, in this case, P of lambda is not a valid distribution. Because if you just integrate P of lambda from negative infinity to positive infinity, it just gives you infinity or negative infinity, whatever, right? It just gives you infinity because this guy must be negative. Right? So we call this kind of uniform distribution as an improper prior because it's not a really valid prior distribution. However, if we use that to shove into our joint distribution, meaning that I multiply with my likelihood and then I normalize it and I can compute the posterior distribution. If the posterior distribution of lambda given x is still a valid distribution, then it is acceptable. That's why we call this as improper prior. As long as the posterior is proper, we can still use the improper prior. But is the uniform distribution perfect? Intuitively, it's perfect, right? Intuitively, it doesn't represent anything like that. We kind of like make some compromise will allow improper uniform prior distribution, right? And it looks like everything is solved, but actually it's not. Right? There's some kind of property of the uniform distribution which is not good, right? Making us to seek for alternative uniformity graphs. So the problem of the uniform distribution is that it doesn't have the translation invariance. So what does it mean for translation invariance? Let us consider this like general form. P of lambda is proportional to some constant, right? So now suppose lambda is further represented by another random variable eta, like lambda is simply equals to eta squared. Right? So ideally, we know that okay, P of lambda is kind of uniformity, right? The prior of lambda is uniformity, uniformity, right? The prior of eta should be uniformity as well, right? So in other words, we expect that P of eta should be proportional to some constant as well. Right? However, it is not. Right? This can be seen that by using just the random variable transformation, right? If you want to look at the density of eta, right? We just apply the formula we discussed before, right? We just multiply the density of eta times the absolute value of the derivative of lambda over eta, right? So know that d lambda over d eta, which is just the 2 eta, right? And here p lambda, the prior density of lambda is actually proportional to some constant, right? So you multiply a constant with 2 eta, so that means your prior distribution of eta is proportional to eta. But basically says the larger the value of eta, the larger the prior density, right? Obviously, it biases toward large values of eta. It is not uniform, it's not uniformity at all, right? Does it make sense? Right. This is an issue, right? So ideally, we want, okay, even I do some kind of translation of lambda, right? I want to represent lambda in terms of third random variables. Right? If lambda itself is uniformity in the prior, then eta should be uniformity as well. And unfortunately, it is not. Right? We can see that doing some translation, making the prior density of eta proportional is not uniform at all. How can we address this problem? Right? So the problem is when we do variable transformations, the prior is no longer uniformity, right? And the natural question is that how do we construct an uniformity prior, which is invariant to the translation? So here we want to take this important properties of translation invariance into account. So let us consider two commonly types of translation invariance. The first is called shift invariance. So what is shift invariance? Suppose your likelihood takes this form. So P of x given lambda is some probability density f. The input is just difference between x and lambda. So what does this likelihood tell us, right? It tells that, okay, if you shift x and lambda by the same by the same location like C, right? Actually, it doesn't change the likelihood at all. Right? Your Px hat given lambda hat equals to Fx hat subtracted by lambda hat is the same as x minus lambda, right? So actually, it doesn't change if you shift the observation x and your prime lambda at the same amount of location, right? So if we want to construct a uniformity prior for this, right? So now that the likelihood tells us, okay, this shift invariance, to make our prior to be as least influenced to the posterior as possible, I want to make our prior to be consistent with the likelihood, right? That means I want to make the prior to be a shift invariance as well. Now, how can we construct an uniformity prior with which is invariant to the shift? So we want to construct a prior that reflects this shift invariance. Why? Because when it is more consistent with the likelihood, the prior is less influence on the posterior. So this is a key idea, right? So now if we want to construct a prior, its shift invariance, it just means we want to choose a prior that assigns equal probability mass to an arbitrary interval A and B as to the shifted interval A plus C and B plus C, right? So that means, okay, we got the density here, A and B, right? If you move this interval to here, A plus C and B plus C, the probability mass over the new interval doesn't change. Right? So now let us try to derive this form of this shift invariant prior, right? According to our specification, right? So we know that if we want the P of lambda to be shift invariant, that means, okay, if you pick up arbitrary interval A and B, right? The mass, the probability mass over this interval is exactly the same as you move the interval A and B by a position of C, right? So that means the mass, the probability mass in the interval A plus C, B plus C is the same, right? So if you use some kind of like integral variable transformation, right, we can define lambda to be lambda hat plus C and d lambda equals to d lambda hat, right? You see that actually this guy equals to this guy, and this integral equals to this integral for arbitrary A and B. That means the integration function must be the same. Means that P of lambda should be a P of lambda plus C for arbitrary C, right? Of course, yeah, for arbitrary C. So what kind of probability density can satisfy this? Of course, you have to assume that your P of lambda is proportional to some constant, right? Otherwise, you won't. If it is not constant, it kind of vary along with lambda values. You can always pick up C, which can reflect the difference, right? Any question? Is everyone comfortable, right? So we can see that, okay, actually, the general uniform distribution we have discussed only satisfy the shift invariance, but doesn't satisfy another type of invariance. We just give an example, right? If you assume lambda equals to beta squared, it doesn't reflect the invariance, right? But for this shift transformation, it satisfies. It satisfies the invariance, right? So let us look at a particular example, like for Gaussian likelihood. If we look at the mean parameter mu here, right? So we can see that the likelihood itself is Gaussian probability density. Essentially, it's determined by the difference between x and mu, right? So that means the likelihood is the shift invariance. So so to construct uniformity prior over mu, we want the prior to be shift invariant as well, right? So so that means we should choose P of U to be the uniform distribution, right, which is proportional to some constant. Right? And an interesting contrast will be to the conjugate prior. Right? So for the conjugate prior of mu, as we discussed previously, it is another Gaussian distribution. Right? A Gaussian distribution over mu, right? So we actually found that our uniform multiplier over mu is actually proportional to a constant, and the conjugate part essentially is a Gaussian distribution, right? So we can see that actually, if you set the variance, the prior variance of mu in the conjugate part goes to infinity, then the conjugate part converges to the uniformity part, right? Because this is typical Gaussian density, right? So if you make the variance larger and larger, then this curve becomes flatter and flatter, right? If your variance goes to infinity, this curve becomes flat, right? Now and then it becomes constant to the uniformity part. Any questions so far? Okay, great. So next, let us look at another type of translation invariance, which is called skew invariance, right? So what is skew invariance, right? If we take a look at the likelihood, right? If the likelihood has this form, so the likelihood is determined by this parameter sigma, right? So it takes a form which is proportional to 1 over sigma fx over sigma, and sigma is positive, right? And f normalized regular means that f is a valid probability density, means that okay, if you integral with f, it's just give you 1, right? And also, if you integral this likelihood with respect to x, will also give 1. So it's a valid probability density. So this form of the likelihood actually exhibits the so-called skew invariance. So this means that, okay, if I amplify both the data x and the parameter sigma with c, right? I mean, amplify means it's kind of like general meaning that amplify c could be bigger than 1 or could be less than 1, right? And then you multiply x and sigma with the same constant, right? And then your likelihood can be rewritten in this way. So it is 1 over the sigma hat times f, the ratio between x hat and sigma hat. And x hat and sigma hat is just the skewed data observation and the skewed parameter. And this is also a valid distribution. So meaning that, okay, if you just integrate this guy with x hat, it'll give you 1 as well. This is called skew invariance. Why is skew invariance useful, right? Actually corresponds to like a common example for this is like if you want to translate data into different units. Like for example, if you measure something in terms of metric system, I think in terms of American system, right? Like if you use kilometers and use miles, right? You get 2 rates, right? And if you change your parameters accordingly by the same skew, 1 mile is 1.6 kilometers, right? If you switch from American system to kilometers, right, to the metric system, right, you multiply the same skew with the parameters, then you don't need to change the form of likelihood at all. This is very important, right? If you have this, problem, it will make your life a lot easier, right? Otherwise, you have to think about, okay, what should I add some constant in terms of previous likelihood, all kinds of stuff, right? And if you do this, it doesn't need. Right? You just multiply the same skew of both the parameters and the observation. You translate them into a different measurement system, right? And the likelihood function doesn't change. And then suppose in this case, like if we want to assign some uninformative prior over the parameter sigma, right? I want my prior reveals the same kind of skew invariance. What does it mean? It means that, okay, no matter what kind of range, like what kind of interval A and B, the probability mass over this prior, right, should be the same after I reskew this range by some constancy. So basically, if you pick up an arbitrary interval A and B, right, if I want to construct an infinite prior, which reflects the skew invariance, I would expect that, okay, my probability mass over this interval is the same as the probability mass after I reskew this interval by some constancy. So that's the idea. So the problem is that, okay, how do we get some general form to fulfill this kind of skew invariance? As we just did, right? We just want to derive a general form of the prior P of sigma, which satisfies this equality, right? For arbitrary choice of interval A and B, right? The integral over A and B should be the same as integral over A over C to B over C, right? Then let us try to derive what kind of general form can we get, right? Again, from this guy, we can still use integral variable transformation, right? I can define a new variable sigma bar to be C times sigma so that, you know, the limit, the lower limit, upper limit of the integral will become the same as A and B, right? And then you do some kind of variable transformation. Of course, you have to do the variable transformation in the D sigma as well, right? So eventually you'll find that for arbitrary A and B, you should have a P of sigma to be the same as P of 1 over C sigma times 1 over C. Namely here, right? So what kind of P of sigma will satisfy this? Your P of sigma needs to be proportional to 1 over sigma. So you can test this, right? You can test this. You can try to substitute this back into it, and see what happens, right? So if P of sigma is proportional to 1 over sigma, then P of 1 over C sigma will be proportional to anyway, I will leave it as an exercise for you guys, right? But don't forget to use the variable transformation, right? And you will see that P of sigma, when it is proportional to 1 over sigma, this equality will hold. Okay. So now let us look at a concrete example. Right? We still want to look at a Gaussian likelihood, but this time want to look at the standard deviation parameter. So given the sigma, we know that the Gaussian likelihood essentially is proportional to this guy, right? 1 over sigma and e to the power minus half x minus mu over sigma squared, right? So you can see that this is essentially satisfy the form we have just seen, right? So we want to look at the likelihood. Sorry. It's proportional to 1 over sigma and x minus x minus sigma, right? X over sigma, but here we're gonna assume like x is x minus mu, right? So then we can construct uniformity prior. Uniformity prior gives us that P of sigma is proportional to 1 over sigma. Okay. And now we want to associate with the conjugate prior. Okay. So that the conjugate prior over the inverse variance we have discussed before, which is the gamma distribution, right? And inverse variance essentially is 1 over sigma squared, right? So here, given this uniformity prior, right, we do some kind of variable transformation, we can get the prior over the inverse variance lambda, which is also proportional to 1 over lambda. Right? Again, I want you to show this, right? I want you to derive this P of lambda according to P of sigma. Right? And then if you look at the form of conjugate prior of lambda, we know this form it is a gamma distribution, so it's proportional to lambda to the power of a minus 1. A and b are two parameters of this gamma distribution, and e to the power of b lambda. Right? So now, to contrast these two prior distribution, what can we observe? Obviously, if we set a and b to be 0, right, the conjugate prior becomes the uniformity prior, right? So this is another interesting connection between the conjugate prior and uniformity prior, right? In this case, right, for the skew invariance case, for the Gaussian likelihood, we found that the conjugate prior, or the uniformity prior is a specific setting of the conjugate prior. Right? Okay, any questions so far? Is everyone comfortable with this? I think this is kind of like intuitive and straightforward. So just go through it smoothly, right? But let me know if you feel any uncomfortable stuffs. Okay, so next we're going to talk about an even more general uniformity prior, right? So we talk about we want our uniformity prior to be a translation invariant, right? But so far, I only talk about two types of translation, right? One is shift invariance, the other is skew invariance, right? But there could be other types of invariance, like why not I just move by a particular location, or I just multiply by skew, right? What if I do some nonlinear transformation? Right? For example, if I have some random variable theta, right? What if I want to do theta square, right? What if I want to do both shift and skew, right? Like alpha theta times c. All kinds of transformations is available, right? So the question is there any uniformity prior that is immune to all kinds of translations? That part is from Jeffrey's part. It's very smart discovery. Okay? So Jeffrey's part is defined as follows. Again, this is an improper part. So that means it doesn't guarantee that you integrate out theta, which will give you 1, right? But the Jeffrey part is defined as the square root of the absolute value of the facial information. So what is facial information, right? Facial information is defined as the expectation of the random variable x of the second order derivative of the log likelihood. So x, here's the random variable, theta is a parameter, right? So you got the log likelihood, right? You just take the second order derivative of the log likelihood with respect to theta. And remember, this is still a function of x, so you can compute the expectation with respect to distribution of x, right? And you take a negative value. This is your facial information, right? And then you just take actual value of the facial information, take half root, take the square root of it, and it is what your Jeffrey prior is. Right? So is anyone feel uncomfortable about its definition? It's a little bit complicated, but this is what it is defined. And here we only talk about the scalar case, mean that we assume that, okay, theta is a number, theta is a scalar, it's not a vector, right? If it is a vector, right? If it is a vector, then this guy is not a scalar anymore, it's a Hessian matrix, right? And then this guy becomes the absolute value of the determinant of the facial information matrix. And for simplicity, let us just talk about the scalar case, right? And this expectation is taken with respect to the probability of density of X given theta. Right. Any question regarding the definition? Okay, so so let us give some concrete examples about Jeffrey's prior, right? Given its awkward form, right? Maybe if you look at it's not that awkward, right? So we can first use binomial likelihood as an example, right? So binomial likelihood or binomial experiments mean that, okay, if you do a Bernoulli experiment, meaning like you toss a coin, right? And you do it for n times, right? How many, and then we're interested to say how many times out of these n experiments you see the heads, right? So the binomial likelihood follows the binomial distribution, right? Parameterized n the number of experiments, and also theta, which is the chance that your coin you see the head on your coin, right? So the probability density of the binomial likelihood, as we discussed before, right? You have a combinatorial number. You need to look at the combination, the number of possible cases where out of your experiments you see X heads, right? And for each case, the probability is theta to the power of X times 1 minus theta to the power of n minus X. Right? So let us construct a Jeffrey's prior or theta. Right? According to the definition, we need to compute the log likelihood, right? So first compute log likelihood because we are only interested in theta, right? So you can just throw out this constant, right? So it's x log theta plus n minus x log 1 minus theta. Then we need to take second order derivative of the log likelihood, right? Which is straightforward, which gives you this guy, right? Minus x over theta squared subtracted by n minus x over square of 1 minus theta, right? And then, according to the definition, right, the Jeffrey's prior is defined as a negative expectation of the second order derivative, right? So this is second order derivative. If you put negative sign in front of it, you got this guy, and this guy becomes positive, right? So then you take expectation, right? Here we're going to use a very well-known property of the expectation, right? So expectation of the binomial random variable is just the n number of experiments multiplied with theta. Right? So now you get that your I theta is actually proportional. So it should be proportional here, right? So n theta expectation here, right? Plus over theta squared plus n minus n theta is expectation here, right? So over 1 minus theta squared, right? So just do the term of to the margin, right? So eventually, this is a mutual information. Sorry, this is a mutual. This is a feature information. So the feature information is actually n over theta times 1 minus theta. Right? Then your Jeffrey's prior is proportional to the square root of the absolute value of the feature information. So that means you just take the square root of this guy. So it's proportional to theta. Remember, n is constant. You can throw it out, right? So, so the Jeffrey prior of theta is proportional to theta minus half. Just need to look at the denominator here, right? Theta minus half multiplying with minus theta minus half. This is actually a beta distribution, right? So remember, beta distribution in B is proportional to theta e minus 1 and 1 minus theta e minus 1, right? So if you look at form here, so we know that A and B are both half. So what does this Jeffrey prior reflect? Right? Otherwise, what does this beta prior reflect? And why it is uninformative. So we can look at this concrete example, right? This is our binomial likelihood, right? And this this blue curve corresponds to our Jeffreys prior, which we just derived. This beta is a beta distribution with parameters half and half, right? On the other hand, like if we just use uniform distribution, right, which is correspond to beta distribution with 1, 1. So you can see that for the uniform distribution, you got a flat red line, right? So you might be confused, right? Looks like the red line is more unbiased, right? The red line is more uninformative than the blue line, right? The blue curve. Why? Because the blue curve obviously put much more density at two ends, right? And put very small, not very small, but just a much smaller density in the middle, right? But then why we should prefer the blue curve? Here is the rationality. Again, to make the prior to be uninformative doesn't mean like you should make your prior to be totally no information. Instead, our goal is want our prior to be as less influential to the posterior as possible. How can we do that, right? We want to make our prior to be consistent with the likelihood as much as possible. In other words, we want the property of prior to match the likelihood. Right? So if we look at the likelihood, like it's proportional to this theta x, 1 minus theta n minus x, right? So what kind of theta value make the data takes the least effect or even no effect? I mean, if I choose some kind of theta, no matter how different x values are, the likelihood doesn't change. Is there such a value of theta? Any thought? Let's just use theta equals to half. If theta equals half, what will happen to the likelihood? You know, theta will be equals to 1 minus theta, right? Because theta is half. So that means x, we can merge the exponent, right? X plus n minus x. So if theta equals to half, right? So now it will become theta to the power of n, right? Why? Because theta is half, 1 minus theta is half, right? They share the same base. So the exponent is just merged together, x is cancelled. So that in this case, right, no matter what x is, what observed data x is, the likelihood doesn't change at all, right? In other words, the theta takes the value of half. The theta takes least effect. This has almost no effect, right? And what kind of theta can make theta takes the greatest effect? Of course, when theta is close to 1 or close to 0, right? When theta is close to 1 or close to 0, any change of x, right? Any change of x obviously will change the likelihood largely. Right? Does it make sense? Right? When theta takes value, right, takes value to be half, right? We see that okay, x has the observed value x, the observed data x actually has least effect over the likelihood. However, when theta moves towards 1 or moves towards 0, you can see the influence of the data to the likelihood becomes larger and larger. So now if we look at our blue curve, actually it exhibits the same effect. Okay, so you can see that in the middle, when theta is equal to 0.5, the prior takes the minimum, right? It is the smallest, right? Prior density is the smallest. When theta moves towards to the two ends, right? The influence on the prior density becomes larger and larger, which is consistent with the influence of x on the likelihood. That's why using this Jeffreys prior over theta is more reasonable, because it tries to match how the data influence the likelihood. And then, because it is consistent with the likelihood, so the posterior will be mainly determined by the likelihood. Right? On the contrary, if you use a different prior, right, which has drastic difference with the likelihood. So you can imagine when you integrate the prior and the likelihood together, get a posterior, you kind of like fierce combat between the two, right? So the posterior will be highly affected by the prior, right? So this is the underlying rationality. Any question? Okay. So next, we want to show that why Jeffreys prior is invariant to any translation. To show this, right, we can consider a kind of general translation H, right? So I know I construct a second random variable phi, right? Is a transformation of theta, right? Through this function H, right? So if we can show that the Jeffreys prior over phi is the same as you use random variable transformation for theta, and where theta is also a Jeffreys prior, then we show that okay, the Jeffreys prior is invariant to any translation, right? So we know that okay, if you want to construct a Jeffreys prior over phi, we know that okay, by definition it should be half root square of the Bayesian information of phi, right? But because phi is obtained from h of theta, right? We know that theta is Jeffreys prior as well, right? Then by some variable transformation, right? You want to look at okay, what is prior of h theta, right? If prior h theta also follows this, that means okay. That means okay, after this transformation, it's still Jeffreys prior, right? So we can examine that, right? So, oh, okay. Let's stop here today, right? It's already 5, yeah. Okay, let us wrap up this on next Tuesday.